Okay, today we're going to cover singular value decomposition after the Jordan form. So in brief, overview is that diagonalization is for a symmetric, and for normal matrix we can write in this form as eigenvector in the column, eigenvalue, and eigenvector in the column. This was diagonalization. And in case A is defective matrix, not normal, defective matrix, it cannot be diagonalized, so we, not J, T, let's say T. It can be, it's shown that there exists M and T. A and T are similar matrix, and T is triangular matrix, upper triangular matrix. Among the upper triangular matrix, we may select the most simple form, that was Jordan form. So among the triangular matrix, we take Jordan form, which is constituted by Jordan blocks. Each Jordan form, each Jordan block is constituted by corresponding eigenvalue and 1, and all other components are 0. And of course it's triangular matrix. So it's as close to diagonal as possible. Okay, so this is maybe the generalized version of diagonalization. But this and this still for square matrix. But what about rectangular matrix? And more general than those are singular value decomposition. So a matrix A can be decomposed by U sigma V transpose. Here, U is orthogonal matrix, so its columns are mutually independent, and each column length is 1. And sigma is here for given m by n matrix, m by n, so it's rectangular. Then U is m by m, m by m, and n by m. V is n by n. Also, V is orthogonal matrix. Square, square. This is a rectangular matrix. And on the diagonal component, because this is rectangular, there is not exactly diagonal component, but right on here, singular values are located. Those are singular values. Here, it was eigenvalues, right? Here, we had eigenvalues on the diagonal, but here, nearby diagonal, they are singular values. So it's singular value decomposition, and it's m by n. So m by m, m by n, and n by n makes m by n original matrix. So even though A is rectangular, still we can decompose it in this form. That's singular value decomposition. So section M is singular value decomposition. This singular value decomposition reveals the very substantial property of matrix A. Very substantial properties for matrix for A. And I think its application is larger than diagonalization and larger than similarity transform. And also, that means if you can model your system in linear, as a linear component, then you can constitute a matrix A, and using the singular value decomposition, you can reveal the substantial properties of your system. So singular value decomposition is very, very important and useful. So first, let's compare this singular value decomposition with diagonalization, because we are already got accustomed to diagonalization. Diagonalization and singular value decomposition. And the diagonalization, A is a square matrix and given like this. And in singular value decomposition, it doesn't need to be square matrix. It's given like this. So A is square and A is rectangular. Here, S is orthogonal matrix. So S inverse is equal to S transpose because it's orthogonal matrix. Here, UV is also any orthogonal matrix. And U transpose U equal to V transpose V equal to identity. And lambda is a diagonal matrix with lambda I on the diagonal position. Diagonal components are lambda I. And here, if the rank of A is R, then we define R singular values. We have R singular values, and they comes to the diagonal part of sigma. Sigma is a rectangular matrix, so they goes to on the diagonal part. Here, 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 if its rank is 4. Now, let's go to definition. Okay, any arbitrarily matrix A, m by n, can be factored into A equal to U sigma V transpose, orthogonal, diagonal, orthogonal. Orthogonal, diagonal, orthogonal. Then the columns of U they are eigenvector of AA transpose. And the columns of V, they are eigenvector of A transpose A. And R singular values for the rank R, they go to on the diagonal position of sigma. And it's square root of eigenvalue of A transpose or A transpose A. So thinking about A transpose or A transpose A, they are square, right? They're square. A is rectangular, but A transpose or A transpose A, they are square. So this is square matrix. Also, this may have specific lambda eigenvalue, and singular value is square root of eigenvalue square. So its sign may be changed. If for negative lambda, it will be turn out to be positive singular value, something like that. Sign will be changed. And let's take a look at some properties for remarks one by one. For positive definite matrix, if a matrix is positive definite, then their eigenvalues are positive. All eigenvalues are positive. For a positive definite matrix, sigma is equal to lambda, and also singular value decomposition is equal to S inverse S, S lambda S inverse. For other symmetric matrix, any negative eigenvalue turn out to be positive singular value. So negative eigenvalues in lambda is positive singular value in sigma. For complex matrices, singular value remains real, but UV becomes unitary. UV are unitary. Unitary is complex version of orthogonal matrix. So just in real domain is orthogonal matrix. If it's complex, then it's unitary matrix. And for unitary matrix, similar to orthogonal case like this, U Hermitian U equal to V, Hermitian V equal to I. We have this kind of relationship, which is H is transpose with complex conjugate. Then, of course, it's true that U sigma V H. You can write. This is singular value decomposition for complex cases. And remark 2. U and V have contains eigenvectors of AA transpose is remark 2. Eigenvectors of A transpose and A transpose A is in the column of UV. First, take a look at the U. If we have AA transpose, then A is U sigma V transpose. A transpose is V sigma transpose U transpose. Then they are identity. So U sigma transpose U transpose. Then it's natural that this matrix AA transpose is decomposed in diagonalization form, right? Something transpose and diagonal component. This is n by n. This is n by m. So this is diagonal matrix. That means if this is diagonalized form, then its column is eigenvector of this matrix. So column of U is eigenvector of AA transpose. Are eigenvectors of AA transpose. Similarly, V case, if we do the A transpose A, then V sigma transpose U transpose, U sigma V transpose, which is V sigma transpose sigma V transpose, still the diagonal 4. So you may say columns of V are eigenvalues of A transpose A. Here, in the sigma, this is square matrix, and in their diagonal component, sigma square values are allocated. So sigma value, singular value square is eigenvalue of A transpose, or eigenvalue of A transpose A is a singular value square from this relationship. So we have seen that U and V have specific relationship with A. Then, does U and V have other specific relationship too? The answer is, of course, they also have a relationship. Here, U and A have some relationship, V and A have some relationship, and U and V also have relationship. That's remark 3. U and A have a specific relationship that AVJ equal to sigma J UI. Sigma J UJ. If we take jth column from U and the same jth column from V, and they have this kind of relationship for jth singular value. So each column have a relationship through the singular value, corresponding singular value to A. And A, U, V, and their singular values are, I may say, harmonized in some way. All the components are here, right? A, okay, A. U, singular value, V. So they are related in some way. The proof is easy. A transpose A, its eigenvector is Vj, right? Its eigenvector is Vj. So eigenvector and eigenvalue. Eigenvalue is sigma J square. Eigenvalue is sigma J square. So we have this kind of relationship. Then let's multiply A on both sides. Then A transpose A Vj equal to, this is scalar, so it can come to the front, A Vj. Now, if I put like this, AVJ is, by this form, AVJ is eigenvector, because this is the eigenvalue, original matrix, eigenvector of AA transpose. by this form itself. So given this form, we can say AVJ is eigenvector of AA transpose. And eigenvector of AA transpose is UI from here. Right? They are UJ. Then let's think about the length of AVJ. We need to consider length because it's eigenvector, but UJ is unit length. So UJ is unit length, but we cannot guarantee that whether AVJ is unit length or not. So we cannot say they are equal. They are equal up to scale. So AVJ is equal up to scale. So there should be some scaling factor, let's say delta UJ. If this is unit length, then this is 1. Otherwise, we need to set specific delta. This is unit length. This cannot be guaranteed as a unit length. So we need to check the length of this, AVJ. Length of this AVJ is, length is checked by inner product. So AVJ transpose AVJ. So VJ transpose A transpose AVJ. It's length. Then this is given to be from here. If we multiply VJ in front, then VJ A transpose A VJ, VJ A transpose A VJ, and VJ sigma J square VJ. So it's VJ sigma square Vj. So you can see that its length is sigma. So this is inner product. So A Vj is square is equal to sigma j square, which means sigma j, which means its length is sigma j. So we can say that if I put sigma j, then they are equal. That means AVJ equal to sigma j uj. So we prove that AVJ, sigma j, uj are harmonized in some way, not on arbitrary choice. But if they are decomposed, then they make some specific harmony. U and V also have specific harmony. And remark 4, personally I like the first remark best because if there's U and V, if the matrix is m by n for, let's say in this case m is larger than n, so m by m, n by n. So m is large, n is small. And here's U1, U2, blah blah blah, Um, and V1, V2, blah blah blah, Vn. Okay, if we do the singular decomposition like this, then let's say the rank is R, then first R columns. First R columns is column space of A. Basis of column space of A. They are basis of column space. And remaining M minus R, then what it will be? Column space and then left null space. This is basis of left null space. Then the first R is similarly basis of row space. Basis of row space. And remaining n minus r columns are basis of left null space or null space. It's a very beautiful property, right? It's very beautiful property that UVR basis of fundamental for subspaces. What a beautiful property. Then, in case you want to find some specific null space or specific, if you want to constitute some specific fundamental subspaces, you can just do the singular value decomposition. Then you find their basis. Especially, one very useful property, one very common in optimization is this thing, null space. Because in many engineering application, you may want to make them nothing, AX equal to nothing. You may want to find X that may give nothing. But because of various noises, nothing does not, we cannot find any solution like this, but we want to minimize X as much as possible. Then, what's the X? If something is written like this, what's the X? X is basically null space, right? If I give any null space xn, then it will go to 0. Then, if I have, like here, if I have multiple bases of null spaces, let's say V, let's say 3, 4, 5, for example. If null space is all 3 dimensions and they are bases, then each of them may have corresponding singular value. And let's say that they are ordered, largest and smallest, for example, 3, 2, 1, for example. Then, if I put this here, it will have minimum singular value. So it will give a specific epsilon, not 0, but that epsilon will be the minimum achievement that we can acquire. So that's, we may say, optimal. So although there's no X, it can be optimized by using V5, the last column of V, because last column is one of the null spaces, and if we order the singular value from in decreasing order, then the last column may give the minimum value. So it could be very useful in doing minimization or optimization or whatever. So let me show you the real example that what if A is given to be, screen is here. 녹화? Okay. Now let's do the singular value decomposition for this kind of matrix. So for this kind of matrix, it's natural that the maximum rank is 2, right? Because there are 2 columns. Maximum rank is 2. And it seems like that one factor is very large. So we may imagine that there are 2 singular values. One may be larger than the other one because one component is very large. So if we do the singular value decomposition, we have U and U as U1, U2, U3, and diagonal sigma as 1 is 99505.002.2100, and V is V1 and V2. Then from this we can see that M, because it's rank 2, they are column space, basis of column space. This is left null space. And one singular value is very large, and the other singular value is small, relatively small. So given input, if input is given, that will be scaled according to, they'll be scaled in one specific direction, because this is very large. It will be scaled in its corresponding direction in large. And we can see that this is row space, and we can expect that no null space and row space. Then let's see in figures. Okay, this is row space. Red lines are row space. So red line is row space, and you can see that green is input. Green is input. And here green is output. So red is row space. I just plot the columns of V. And because there's no null space, any arbitrary input is combination of those two. And you can see that it's R2, it's plane. So you can see that it's plane. If I rotate it, it should be plane. So you see it's plane, right? It's R2 space. There's no null space. And I gave the input as linear combination of those two. But because one singular value is very large, here it should be scaled in one specific direction. And that direction is combination of column space, because the answer is always lies in column space. Here, red is column space, and blue is left null space. We have one left null space. So column space should be orthogonal to left null space. So in three-dimensional view, you see that it's not easy to visualize, but you see that green is elongated, enlarged in specific direction because of this singular value. And you can check that this green line lies on two combination of red lines. And you can check that the blue line, which is null space, left null space, is orthogonal to not only green line, but also red line. You can do the inner product between those vectors, then you may be able to verify what's going on. As I turned on the projector, I may keep going to more examples. The other possible example is image compression or whatever compression. We'll consider that it's application 1. It's decomposed in this way, which is U1 sigma 1, U1 transpose, V1 transpose. U2 sigma 2, V2 transpose, blah blah blah. UR sigma R, VR transpose. Okay, if an image is A is naturally, this could be an image, right? Because it's 2 by 2 matrix. So any image can be represented as rectangular matrix. Given that image, we may do the singular value decomposition, and we may order them in decreasing order. So if it's 2506 by 2506, then there should be 2506 sigma values. Then we may order them according to their size. And if we take just from something, the largest of few coefficients, let's say if they modeled, for example, let's say this is 9. Let's say this is, for example, 80. Then with the 4, let's say the total is 100. It doesn't need to be 100, but let's assume that total is 100. And the 4 factors constitute about 90.1 values out of 100, out of total sum of sigma values. Then we can say that using those 4 coefficients, we can restore or we can compress the original image up to 90%. For example, okay, I'm using just one largest singular value and representing image. Okay, this is one largest singular value based image for the given original 256 by 256. Then let's use 2 largest base. A little bit better. Let's use 4 largest base. Let's use 8 largest base. What's this? Monkey. With the 8 coefficient, we are able to recover this kind of figure. More 16, with 16 coefficient, more realistic. With 32, more realistic. With 64, almost the same. With 128, okay, so with 128, we have this kind of image. Nearly equivalent to the original image. The original image is here, monkey. Its size is 88 kilobytes. This size is 88 kilobytes. But this size is just 128 times 4 bytes. Far smaller than the original figure. But the quality seems to be basically the same, right? For human being. Or I may say, here one important thing is those things, U1, U2, U3, UR, or those things are orthogonal matrix, which means they're mutually orthogonal. Here, also they are mutually orthogonal. So it's something like using the mutually orthogonal basis, we can represent original signal using as a linear combination of mutually orthogonal functions. This is linear combination of mutually orthogonal functions. So they are mutually orthogonal something. And sigma gives linear combination, just scaling. So in engineering, it is very, very good to do the linear it's very efficient to model a specific something as a linear combination of orthogonal functions. One example is Fourier transform, right? Fourier transform is a linear combination of orthogonal sine and cosine. Or, if I show you one more example, okay, this is from a paper in NIPS from Dr. Park at Carnegie Mellon University. And here, what he did is that given arbitrary signal, given arbitrary time-based trajectory signal, and it's their time-based motion, x, y, z, blah, blah, blah. As time goes on, the motions are stacked on a vector. And they can be approximated as beta 1, theta 1 is a function, and beta 1 is scaling. And theta 2 is another function, and they should beta 2. Beta 2 is another scaling. Theta 3 is another function, and beta 3 is a scaling. So it's a linear combination of theta 1, theta 2, theta 3. And here important thing is that theta 1, theta 2, theta 3 is orthogonal functions. They don't have any relationship, mutually orthogonal. Then this kind of signal, original signal, can be approximated as a linear combination. This is scale coefficient, right? So linear combination of orthogonal functions. So again, we have linear system, simple linear system. Then with this, we can model any arbitrary motions. For example, here, drunken people. He got drunken. As he was drunken, his motions are very arbitrary. Fall down. Okay. As we increase the number of bases, so he increased up to 228 coefficient. But if we take a look at it slowly, using just 50 coefficient, most motions are already modeled nicely enough. One more time. So for given this very arbitrary motions, okay, here the number of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30, 40. Okay, 40, good enough. Just 40 coefficient, then the arbitrary motion can be nicely reconstructed. So this is one of the very useful thing in engineering, that arbitrary signal, first, arbitrary signal need to be linearized in whatever way. So this is already linearized something, and in front, he linearized this arbitrary signal in this way. If it's linearized, then we can model the original signal in a way that by combining as a linear combination of orthogonal functions. As a linear combination of orthogonal functions. Then we can very efficiently model the signal. And let's jump to application 5. That's this is a paper about using singular value decomposition, and its citation number is very large, an algorithm for associating the features of two images. So here they use singular value to associate two sequential images. So we might be able to extract zero. Here the circle is the feature in the first image, and X is the feature in the next image. Then, just by doing the singular value decomposition, we can easily find the relationships. This paper is not that much complex. Just finding the singular value decomposition, that's it. Using just that singular value decomposition, these kind of rotation or translation or scaling, feature-to-feature matching is easily conducted. So examples are, see, this is example that given circle and given X, although there are many false positives, but you have to think about that. It's not a complex algorithm. It's a very, very simple algorithm. Just singular value decomposition. Only by using the singular value decomposition, we can acquire this kind of achievement. Then, given this initial seed, we might further optimize, further increase the performance. But the starting point is a singular value decomposition. That's it. So this is fifth example. Not only this, there are many, many examples that you might be able to utilize. And let's go to other application. Please turn the light on. 앞에 불 좀 켜줄래요? Application 2. Okay, there's epsilon, very small value. Then, because epsilon is very small value, this is almost equal to 1. This is almost equal to nothing. This is almost equal to 0, 1, 0, 1. So its rank should be 1. However, because of this epsilon, it's turned out to be, its rank is equal to 2. But its effective rank should be 1. To check whether the rank is, this is very commonly, many times we face on this kind of situation because sigma can be noise. Because of noise, linearizing error or whatever, because of those various things, there could be phantom or ghost, like this epsilon, or round-off error, quantization error, something like that. So in this case, we check the single values and we define condition number as single value max, single value mean. This is condition number. So if condition number is equal to 1, then the matrix is nicely organized, so we can trust the rank. But if the condition number is kind of equal to condition number corresponding to very large value, then it's not good to trust that situation. Do I have the paper regarding that? I don't. I don't have papers of now. Oh, here it is. So, here, one of my graduate students is doing the finding plane and matching pairs of planes to do the localization. But sometimes because of slight error, because of noise or wall is slightly distorted, the rank could be larger than the real rank. So he checked the observability and he checked the singular value. You see the equation number 4, that's the condition number. So he checked the observability. Observability we're going to learn in chapter 6, and then it's checking the singular value and checking the condition number according to the angle. So when we can get the best result for two planes, when two planes are orthogonal, then we have maximum information. If the two planes are parallel, we get minimum information. So it's good to have orthogonal planes as much as possible. So here you see that in case it's orthogonal, two planes angles are orthogonal, then we get the minimum singular value, minimum condition number. Then that means good result. Otherwise, it's parallel, then its condition number is very large. That means it's very, although there are two different planes, the information is not that much effective. Or when we do the localization, we check the rank. We try to find effective rank. So you see that here singular value decomposition of some covariance matrix actually is pseudo-inverse of covariance matrix. So pseudo-inverse you're going to cover later. And then U is familiar, right? U something, S something is familiar form. Then we get some kind of check rank, whether check rank is 1 or nothing, or rank is 2, or rank is full rank, or something like that. To do that, we may use the condition number or something like that for the localization. So that makes the algorithm better than the normal cases. Okay. Okay. That's the about condition number. Make it black. Or application 3 is polar factorization. So 2D convolution can be changed into 2 times 1D filtering by polar factorization, AQS. If we do the singular value decomposition, then we can naturally do the polar factorization. And in robotics, there are several persons who do the robotics arm. In robotics, you may do when you do the when you calculate dynamics, if you do that, if this corresponding to stretch and this corresponding to rotation, so you can, given A matrix, you can easily compose them. Or in continuum mechanics, you may use this singular value decomposition for polar factorization, using polar factorization. And in robotics, in mobile robot, there's a scan matching algorithm using polar factorization. But unfortunately, it's not that much effective. So in mobile robot, polar factorization was not that much useful. But in ARM or in ARM control or for manipulation, that should be very useful. And application 4, we have much to talk about. That's pseudo-inverse. Let's say that. Application 4, let's scratch it from here. Okay, least square problem versus pseudo-inverse. Okay, there are many measurements. The vectors that we want to find is not that much long, but there are many measurements. That's one case. And the other case is that The vector we want to find is very large, but the measurement is there are a few measurements. In this case, rows are dependent, right? Rows should be dependent. In this case, column should be dependent. Here, row A, maximum rank, should be smaller than minimum of M and N. Here, N is the small one, so maximum rank is N. Here, row A is same minimum of M and N, and here minimum is N. Here, there's no solution because this B is not in the column space. It's combination of column space plus left null space. So what we do is this is square. A transpose A x hat equal to A transpose B. So we project B, original B, through the A and project it on the column space, and we get our best approximation that gives the least minimum error. So we do the least square. So this is least square based. Here, too much information. Information is too much. So we need to select one of the optimal solution. That's what we did in the least square. Other case is this kind of thing. Then, if the rank is M, for its maximum rank is M. If the rank is M, then null space dimension is N by M. Because N is large, it should be larger than 1, at least. Then that means there is null space. Null space exists. If there is no space, then there are multiple solutions, basically. There are so many solutions. So it's too many solutions. Then among the solutions, what shall we find? If there are multiple solutions, what shall we find? One example is, as I told you, null motion, right? Null motion. Null motion. So given this my arm configuration, this is 7 degree of freedom, but my end position is 6 degree of freedom. So there should be one null space, so I can do the null motion. If there are null motions, what are you going to do? Then one good choice, one reasonable choice is to minimize the null motion, right? Why give excessive, too much null motion? You don't need to do that. So minimize null motion. So in that case, we choose x pseudo as shortest x. That satisfies A transpose A x hat equal to A transpose B. So among the multiple solutions, we choose x, which is the shortest among the multiple x hat, which is the shortest one is x pseudo. And this may minimize the null motion. So that's to find x pseudo, we need to find A pseudo inverse. That gives x pseudo. That can be acquired by singular value decomposition. Let's keep going. So let's think about step by step. We have 7 steps, and one diagram. So first step, the optimal solution of AX equal to B in this case is the minimum length A transpose AX hat, and we denote it as X pseudo. For diagonal case, if A is diagonal, then let's say it's sigma 1, sigma 2, okay, there are too much signals because we can take sigma 3 and sigma 4 for any number, it doesn't matter. So they are basically two null spaces. The natural choice is to take x3 hat x4 as nothing, right? To minimize its length. That's the natural choice. Then our choice may be maybe 1 by sigma 1 B1, 1 by sigma 2 B2, and nothing, nothing. This may be the minimum length solution among multiple x hat, and it can be written as 1 by sigma 1 0, 0, 0, 1 by sigma 2, 0, 0, 0, 0, 0, 0, 0, 0, 4 by 3, times B1, B2, B3. Then we say pseudo-inverse this as pseudo-inverse. Then if A is diagonal, then we can see that pseudo-inverse is just inverse of diagonal elements. If A is, in case A is diagonal. Number 2. Number 2 is consequence of this thing. If for a diagonal, matrix sigma, given the sigma from sigma 1 to sigma r, in any location, it doesn't need to be square, like this, it doesn't need to be square, then sigma pseudo is 1 by sigma 1, blah, 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 1 by sigma r. So it should be pseudo. In your lecture note, it seems like that it's transpose, but it's a pseudo cross. Then, how to calculate its diagonal case? But if it's not a diagonal case, how to calculate A pseudo? Then, let's think about AX minus B. Although we multiply U transpose inside the matrix, its length is unchanged because U transpose is unitary matrix. Its length is 1, so we may be able to multiply U transpose inside. Then its length is still unchanged if we multiply U transpose. Then A is decomposed as U sigma V transpose. Then U transpose gives identity, so it's sigma V transpose minus U transpose B, its length. Then let's put Y as V transpose X. Then, because V is orthogonal matrix, we can write V inverse X because of V's property. Then this we may say, oh, I missed X. AX. So this is what we defined y. So this original equation is sigma y minus u transpose b. Now, sigma is diagonal case. In case of diagonal, its pseudo-inverse is given by this form. So we know the pseudo-inverse of that form. So y pseudo will be given sigma pseudo u transpose b. Here, y pseudo is v inverse x pseudo is sigma pseudo u transpose b. Therefore, sigma pseudo is v, x pseudo is v sigma pseudo u transpose b. Then we say this part as a pseudo. So a pseudo inverse is can be calculated, can be constructed from singular value decomposition. For sigma, we take the inverse in this way, and u is the same but transposed and in the end, and v is in front. So through the a pseudo, you can find minimum x pseudo that's among the multiple solutions in these column-dependent cases. Now, let's say that this pseudo-inverse revert the four fundamental subspaces diagram. I mean, the original four fundamental subspaces were drawn from the row space to column space. Original is this is row space, this is column space, this is null space, this is left null space. So original diagram is starting from here and goes to here. That's original diagram. But pseudo inverse is giving inverse direction. So left null component goes to 0 and column component goes to row in that way. So it's inverting the direction. Let's see that step by step. One, two, three. Given the singular value decomposition, x pseudo is a pseudo b. Then x pseudo is x pseudo may have row component plus null component. X pseudo is combination of row component and null component in general, of course. Now, x pseudo satisfies because x pseudo is one of its solution. X pseudo also satisfies this equation. X pseudo also satisfies this equation for any n. Because n is null space thing, so if I write it, n here, it should be 0. So null space component should be 0. So xn is also part of general solution. Because given xn, xn can be satisfied. And this part goes to nothing. So xn is part of general solution. And there are multiple, there could be possibly multiple xn. Also, x pseudo length is xr length squared plus xn length squared. Because xr row component and null space component are orthogonal. So by the Pythagoras law, orthogonal length sum is the same to its combination's length. And we know that although xn is part of general solution, in the pseudo case, this is already minimized. So if it's minimized, it should be the minimum case among multiple cases. So if it's minimized, then it should be nothing. So in X pseudo, there is no null space component. So in X pseudo, null space component is nothing. So I may write A pseudo B goes to X. If here's B, then A pseudo B is X pseudo, but that X pseudo is not combination. For that X pseudo, null space component is nothing. So X pseudo should be in the row space because there are no null space component. So I may draw 3. A pseudo B goes to X pseudo in row space, as there's no null space component. Number 4 is a similar statement that with the number 3, for the shortest X pseudo, it lies on the row space. So number 4, I may write X pseudo lies on row space. Number 5 is that A X pseudo P is satisfied. So if I set P in the column space, as we projected, if we project B into the column space, we may select P, then we have A X pseudo is P, because X pseudo satisfies, basically X pseudo satisfies this is P. This is X pseudo. X pseudo satisfies the least square solution, right? So X pseudo, here should be A pseudo. So X pseudo satisfies the least square equation. Then although it's not directly go to B, but it can go to P. That's number 5. Number 6 is any B P plus E. Any B is combination of P plus left null component in case B is not on column space. So for arbitrary B, and in this case, because there are multiple solutions, B is on here, and because they are mutually orthogonal, they are orthogonal complements in Rm. They are orthogonal, mutually orthogonal complements in Rn. So B should be linear combination of P plus E. So this is 6. B is linear combination P plus E. 7 is that final statement. It knocks out the left null space, and also it knocks out the null space by choosing SR as X. If we draw a diagram like this, we can see that the null space component is not reflected here. So null space component is knocked out, removed. Left null space component removed, as well as if we take XR as X pseudo, then there's no null space component in here too. So we can draw a diagram like this, and if I invert it in this way, then this diagram is reflection, mirroring of the original diagram. So original diagram is starting from here and go to here, but pseudo inverse diagram is starting from here and go to here, and the same copy with the mirroring, vertical mirroring. So singular value decomposition is basically vertically mirroring the original for fundamental subspaces diagram. So let me think about one example. Okay, AX equal to B, which is there are 3 variables. Then this is, there should be null space. So there could be many solutions because they are null space. This is solution. If we put it, you can see that it's satisfied. This also satisfies it. All satisfies it, and so many solutions. Then, using the equation, this is A, we may be able to do the singular value decomposition for this rectangular matrix, and we may be able to find A pseudo. Then A pseudo is given to be -1, 2, 2, H pseudo, which is finally turned out to be like this. This is A pseudo. Then multiplying A pseudo to B, multiplying 18 here, then X pseudo is given to be 18 here, -2, 4, 4. So this is minimum length solution, which was originally written here. So this is X pseudo, and its length is minimum. Its length is larger than this, its length is larger than that. So this is minimum length solution that satisfies A transpose A, X hat, B. So among the multiple X hats, this is a minimum length solution that satisfies that kind of relationship. Okay, so this is the end of a singular value decomposition, and I may say this is a fruit, very delicious and very useful fruit of linear system theory. So again, if you are able to model the original system or original signal or whatever in matrix form, then you can find their substantial feature, and there are many useful applications, from optimality, blah 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 blah. So I may recommend you to get accustomed to the singular value decomposition. Okay. Functions of a square matrix. Now we return to a square matrix. Again, we return to a square matrix. Motivation is that can we find AK, or can you find exponential k? So if you want to find those things, we may utilize functions of a square matrix. Okay, so let's say this is a function. Function of square matrix is AK, or function of square matrix is EK. Let's say this is function. Then calculating this function is very much computational load. Similar, this kind of situation, it may acquire much computations. Then if we are able to describe this function like this, if we are able to describe a function like this, where this psi a is equal to 0, then this complex function is substituted by a simple function. If we are able to describe this function in this way, where psi a equal to nothing, then complex function is written to be a simple function. Then, given this simple function, we might be able to calculate original complex function. That's the motivation. Then, how to find it? That's the question. How to find a function that when a goes into that function, it goes to nothing. That's what we say minimal polynomial. So, minimal polynomial. First, let's define monic polynomial as a polynomial with 1 as its leading coefficient. Let's define monic polynomial as a polynomial with 1 in its leading coefficient. And minimal polynomial of A is the monic polynomial, psi lambda of least degree. Such that psi a equal to nothing. So this is minimal polynomial that gives nothing, and it should be monic polynomial and its least degree. Then we say that as minimal polynomial of A. finding minimum polynomial using A is a little bit complex because A could be arbitrary square matrix. Now what about finding psi using Jordan matrix? This may be far better than finding this one. Then we need to prove if this is satisfied, then this is satisfied. We need to prove it. We need to show that if this is satisfied, then this is satisfied. Then we can find psi, not for A, but for J. Then we can find it. So let's see whether this is satisfied, then this is satisfied too. So let's consider a square matrix. And let f lambda, just polynomial, arbitrary polynomial. For example, it could be whatever. Let's say this. Given this kind of polynomial, its matrix version, let's define that. Its matrix version is basically the same. Instead of lambda, let's define matrix version just to be the same. So given any polynomial function, this is familiar. But this kind of polynomial matrix is not familiar. But let's say that if given this can be written in this way. It's our choice. It's our choice. So the letter could be anything. I just wrote this, but it could be anything. Then, if A is block diagonal, from this sentence, you feel that, oh, maybe A gonna be Jordan matrix, right? Jordan 4. Okay, anyway, if A is block diagonal, then such that A is A1, 0, 0, A2 in this way, then a function of AK form function could be anything. So if function is AK form, then it's A1K, A2K. It's straightforward to prove it because it's diagonal, block diagonal. This means that FA is FA1, FA2. So, if this is Jordan 4, if we just prove one of it, if we find a function that satisfies for given Jordan form, if it's nothing, then it will be validated on the whole Jordan form. Then, if we find something like this, if it will be still effective for this kind of thing. The flow chart goes like that. Okay, now consider a similar matrix. A hat equal to Q inverse A, Q, or A is Q, A hat, Q inverse. A similar matrix. A and A hat is similar matrix. And still, let's set FA to be AK. Then, this AK is Q, A hat, K, Q inverse, which is, this part center part is Q, F, A hat, Q inverse. Therefore, by the same reason, we might be able to write Q like this. Therefore, given arbitrary matrix, if we say A to be J, arbitrary matrix can be factored into, can be represented as Jordan form. Then, if F Jordan form is nothing is satisfied, then original matrix's function is also go to nothing. So we're going to prove that by setting A, and what we need to prove is not for the whole Jordan form. What you need to prove is it's one block, one Jordan block. If for a given one Jordan block this is nothing, then the total will be nothing. And if this is nothing, the original matrix will be nothing. So let's find a minimum polynomial for one Jordan block. That's what we want to do. So, okay, so we're starting from Jordan form. And examples of minimum polynomial is okay, first we need to define, first let's define Ni as a multiplicity of lambda I. How many times lambda I appears is Ni, multiplicity of Ni. Then characteristic polynomial. Characteristic polynomial is determinant. Determinant, when you calculate the eigenvector, you do the determinant. It's determinant of lambda I minus A. This is what you do when you try to find eigenvalues, right? So that's the characteristic polynomial. It can be written as if specific lambda is multiplied by Ni times, then it could be written like this. Then our minimum polynomial can be written like this. Let's define Ni bar as the largest order of all Jordan blocks. Associated with lambda I. For given one lambda I, there could be one Jordan block or two Jordan block or three Jordan block. There could be multiple Jordan blocks. So let's say Ni bar as the largest order of Jordan block associated to specific lambda I. Then minimum polynomial that we want to find is given like this form. For example, Okay. For whole A1 to A5, lambda 1 is multiplied by 4 times, and lambda 2 is multiplied by 1 times. Then its characteristic polynomial. This is characteristic polynomial is lambda 1 is repeated by 4 times, so lambda minus lambda 1 by 4 times, and lambda 2 is appears just once. So this is characteristic polynomial. Then the minimal polynomial is given lambda 1 is multiplied by 4 times. Ni bar is the largest order. Here, Ni bar is 4. Here, 1, 3. Here, 2, 2. And here, 2, 1, 1, 2. Here, 1. This is Ni bar for each case. And for N2, all equal to, Ni bar is all equal to 1. Then, its minimal polynomial is, for here, minimal polynomial is 4. Lambda minus lambda 1, 4 square, lambda minus lambda 2, and here 3. Lambda 2, 1. Here 2. Here 2. Here 1. Okay, they are minimum polynomial. Then, for given minimal polynomial, we need to show that whether j minus lambda a k equal to nothing, whether characteristic polynomial, this is characteristic polynomial form, goes to 0 for if we set k equal to n bar. Fortunately, this is satisfied, so we say this is nilpotent property. So by the nilpotent property, because it's Jordan form, if we multiply by 3 times 4 in this case, then this form will go to nothing. So its characteristic polynomial, this minimal polynomial will go to nothing. Because here, one of the components corresponding to this case, if we put j instead of this lambda. So because of j's special form, j has its special form, the nilpotent property satisfies, and we can make this form if we put j here, and among the various things, j lambda, this will turn out to be nothing. So we can find minimal polynomial in this way. This is illustrated by Cayley-Hamilton theorem. And let's say the characteristic polynomial in this way, be a characteristic polynomial of A, then if we put A inside to the characteristic polynomial, it becomes an plus alpha 1 a n minus 1 blah 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 alpha n minus 1 a plus alpha n. This becomes nothing. The Cayley-Hamilton theorem says that given the characteristic polynomial, instead of eigenvalue, if we put a instead of eigenvalue, then it goes to nothing. That's quite surprising, right? That this characteristic polynomial gives a polynomial function where if we put a instead of lambda, the matrix combination goes to nothing. So this is, I may say, functions of square matrix that gives nothing. One of the functions that gives nothing. This proof is straightforward. Here, ni bar is smaller than ni, or up to equal, because ni bar is largest order of Jordan block. And given this kind of this kind of form, if I write the characteristic polynomial using psi, minimum polynomial, then there should be something more, remaining terms. If it's small, then there should be remaining terms. If it's equal, this should be identity. Then, this is given to be this form. Here, by the nilpotent property, given this will go to nothing. Therefore, the total thing will go to nothing. So characteristic polynomial, if we put a inside, then it will go to nothing. Then finally, using the minimum polynomial and characteristic polynomial, we want to find ak or ek. Mark 3, find or AK. Then theorem 3.5 is a long theorem. Theorem 3.5 is a long theorem, but I will show you with an example. In example 3.7, compute 100 with a is 0, 1, minus 1, minus 2. Then let's set f lambda to be lambda 100. Its characteristic polynomial will be given this form. Then we define set h lambda according to the order of this. This details are theorem 3.5. In this case, because it's second order, we put beta 0 plus beta 1 lambda, and after setting lambda, h lambda, we use given the conditions, they are the same and they are the same. If I put minus 1 here, minus 100th times is equal to minus 1 here, beta 0 minus beta 1. If I put minus 1 for their differentiation, this is this, and this is beta 1, and this is minus 100. So beta 1 is minus 100. Beta nothing is minus 99. So f lambda can be written minus 99 minus 100 lambda. So fa can be written minus 99 identity minus 100a. So if we calculate it, minus 99 minus 100, 100, 101. This is a 100 times, given this. So you may read through the theorem 3.5. 3.5 is straightforward. There, h lambda is defined. It's remaining part of the original equation. In the beginning of the lecture, I said that q lambda minimum polynomial plus h lambda. This h lambda. So if the original complex function is represented by minimum polynomial, then this will go to nothing, and easy part, simple part remains. This simple part can be generally written as a polynomial depending the order. That's in theorem 3.5. And using that h, we put the conditions, some values, and we do according to the differentiation. Similarly, you might be able to solve example 3.8, where they calculate exponential at for given this kind of then you might be able to find exponential at using theorem 3.5. Okay, then this is the coverage of chapter 3. Okay, so now we can calculate 800 and exponential at using the minimum polynomial.